Good afternoon. Today we are going to continue to talk about the dynamic programming. Last time we have seen the basic idea. The basic idea says there is a recursive problem, turn it into tabulation problem, and think about directed acyclic graph hidden in the whole process. So dynamic programming. We have a problem, and what it is, change or turn into, let's say, turn into into iteration, and there is a directed acyclic graph. So those are two important points to think about. The last example, if I remember correctly, we had last time was this example: find the longest path in a directed acyclic. Graph was just to the approach was to fill the table, which is down below the graph, and we went step by step from left to right in the directed acyclic graph, and each time we filled one particular slot in the table, we looked into a few previous entries in the table and somehow put together the value which corresponds to that particular node or to that particular position, which was the length of the longest path which ends in that particular node. And we can do it in one way, iteratively going from, in this case, from left to right, filling the table. So let's see. Then we had also the longest increasing subsequence, which I have to find. Now, longest increasing subsequence, which is looks like it does not look like anything which is related to any kind of directed acyclic graph, to any kind of graph at all. There is a sequence, and we have to pick an increasing subsequence, which is as long as possible, which contains as many elements as possible. In this case, it is 4, 5, 6, and 7 is at least one possibility. And, well, what did they do? They turned it into finding longest path in directed acyclic graph. How did they do it? Relatively easily. They just did the following. They took the elements of the sequence, put them into nodes in the same order, and then they created a directed acyclic graph in which there is an edge between two nodes if and only if the second node in the edge, the target node value is bigger or equal than the value in the start node. So you get quite densely populated graph with lots of edges. That does not matter. All you have to do is to find the longest path in this graph, because, well, any path in this graph corresponds to a subsequence in which the values are still getting bigger or the same or bigger and bigger. So when you start in 5, you can move again to 5, then you can move from 5 to 8, and from 8 you cannot move anywhere because there is no bigger or equal value than 8 to the right of that 8. So any path in this is a subsequence, which an increasing subsequence. So what we want to do is to find the longest path in this graph, and that's all. And finding the longest graph is finding the longest path is a standard dynamic programming question. So there it is. So today we will see a few more examples of similar reasoning in various, hopefully unexpected situations. So let's jump into those. I have to find it. So knapsack problem. So let's see how that works. What's the problem and how do we solve it? So the problem is relatively simply and naturally formulated. We've got some kind of container with limited capacity, as any container typically has limited capacity. That capacity is known. Let's say it is weight or volume capacity. I'm sometimes talking about weight and sometimes about volume, which might not be exactly the same in real life. Typically people tend to talk about the weight because in that case you are not dependent on the shape of your items you are storing in the container, on the shape of the container whatsoever. So only the weight is important. I sometimes call it volume, and I use the notation VI, like imagine volume, which is proportional to the weight of the item. And you've got the items of some weight, which is here, the weight is proportional, strangely enough, to the volume. So there are big, heavy items and smaller light items, and the numbers, the figures which are on the items represent the cost of the item. So you can see, well, typically, well, it doesn't matter. Typically, the bigger item, the bigger the cost, but sometimes it might not be. So the cost is not related to the size, the volume or weight of the item, not related whatsoever. You can have small items which are very costly and big items which are very cheap or anything between. So there is a set of items. And in this variant of the problem, we've got let's say infinitely many number of items of each kind. You might imagine those are some cans you are going to buy in a store, and from each type of can they have a unlimited supply of, and you've got your knapsack, you've got your container. And what you want to do, you want to fill, or maybe not completely, as is shown here. You want to take some items, store them in your container, and of course you want to maximize the cost of those items which are in your container. So you want to make the most costly load. Most expensive or most profit. This is the cost, or you might think of it as a profit. So we want to maximize the profit, and the profit of what is in the container is, of course, the sum of profits of costs each item in the container. All right, so that's the problem. Typically, problem is easy. Well, you say, well, I will take at most 3.5 kilograms with me, and now we've got those canisters, and you have to check which one you take, which one you load, and of course, the cost should be maximized. So the problem is there, and now what we do? So it looks like it does not look as like a recursive problem yet, and still, well, it is a recursive problem. The next slide should tell us that it's a recursive problem. Maybe they will tell us no, it does not. It just shows us various possibilities. So, well, that's just an illustration. If you take 3 to 4 to 5 times the smallest item with cost, which cost is 9, you get to 45. But if you substitute 3 of those smallest items with 2 bigger items, which cost is 14 and weight is 3, not just 2, so the ratio, I think about it as a volume in this case. So you get to cost 46, and there is even possibility to get to cost 48 and so on. So this is just an illustration what can happen. Probably they say there are some possible loads, maybe some cost is some possibility is missing, like I don't know which one at all, maybe, no. So that does not matter. So 30, 90, 16, probably 30 and 30 and this 14 at the top, that one is missing. So okay, so let's go and try to analyze the problem and find some formulation. Okay. So imagine many knapsacks, many containers. They say, well, with capacities. So instead of having one container like this one, imagine you've got zillions of them. Very small container, little bit bigger container, bigger container, bigger container, and so on till you arrive your final container. 1, 2, 3, and there may be 0. 0, 1, 2, 3, 4. Those are capacities. These capacities. And then what then? And this one is optimally loaded. Optimally loaded. When it is optimally loaded, it is optimally loaded. And how that optimum, the analysis says, how that optimum depends on optimal loads of previous possible, of previous smaller knapsacks. So not just that this is optimally loaded, but all of them are optimally loaded with some set of items which are at our disposal. So there are our items here, there, and from each from this infinite store of items, we optimally load each knapsack. So everything is optimally loaded. So there are those items stacked on one on another, stacked on themselves, and then there it is. Now this what the central part of the slide says that this optimal load is a maximum of values. What do they say? What do they say? How do you do it now? You've got to create this optimal load. Those are ready. Those are completed, and this last we don't know how to do it. It is optimally, but we don't know how to do it. Then you have to try a few possibilities. You have each item, you have different items, and you say, okay, so if we want to load this one optimally, then we take what? We check all possible items because there are some items in here. So we say, okay, take the first item, try to imagine it will be here. And then, of course, if there is this item number 1, somewhere in this one, so that's the same situation as if you take smaller capacity by the volume of that item and look into the previous solution where that first item Knapsack, this previous solution somewhere in here, for example, which capacity is smaller by the volume of that first item. So we will take first item, decrease the capacity of the knapsack by the weight or the volume of the first item. So that means if you decrease it, it is some of the previous knapsacks, and that one is filled optimally. So this is the case. The first line. Take the first item. Take the smaller container. How much smaller? Well, by the volume of that first item, because if you have to fit here the item number 1, then it's the same as if you just cut off the top with the item number 1, and what you are left with is the smaller knapsack. So that the optimum is either this one. You do it either with a first item, and of course don't forget to add the cost of that item, of course, or you do the same with all remaining items here. You try all possibilities simply. Take the first item and see what is the optimal load for the smaller knapsack by the volume of that item. Take another, say, okay, and what if we have the second item here at the top? The order of items in the knapsack is not important, so you might easily imagine that the second item is there at the top, and again you do the same idea, same reasoning. Try to make again smaller. You can do it. Make the final knapsack smaller by the size of that item, and look at the optimal solution of the smaller knapsack. So you do it all the times, and then out of all those values, you choose the best one, and there is the solution. So what they say. Optimum load, the optimum load here is the same problem as the original one. Optimum level of the knapsack of smaller capacity is the same problem as the original one. Of course, now they are talking about how to compute these smaller optimal values. Well, absolutely by the same method. We were concentrating so far on how to get the biggest, the target knapsack, which is the original one, that uses smaller knapsacks. And how do we compute smaller knapsacks? Exactly by the same method. Now they say critical. Finding the solutions can be pre-computed by the standard dynamic programming approach and stored in the in a one-dimensional table. Yeah, there will be the table where in each of these cases we will store the optimum value of the cost, the optimum cost of fill of each of those particular smaller knapsacks. So this will be this one-dimensional table. And now they say something astonishing. It can be viewed as a problem of finding longest path in directed acyclic graph. Well, those are nodes. Each of those will be a node in the dialectic acyclic graph, and the next picture will show us what do they mean by it. Let's see how that works. There are our items 1, 2, 3, 4, which are at our disposal. Now each node in the graph corresponds to one possible capacity, one a smaller, bigger, and bigger knapsack. From any node X to nodes of capacity X plus V1, X plus V2. What do they mean? They mean this middle part. What does it says? It says, well, this is a small. For example, this one with 3 represents a small knapsack here. Okay, so if you are filled optimally, then of course you can adding an item, for example, this smallest one, which costs 9, and which volume is 2. Volume of that one is 9, volume is 2. So that means that you move to the 2 steps to the next volume, to volume 5, and moving there costs you, or your gain, the cost is equal to 9. So that means you've got the knapsack number 3, so the volume of weight, or capacity equals 3. There it is, and it is optimally filled. We don't know how it is optimal, no one knows, but it is optimally filled. And then, well, if it is optimally filled, then when you take a bigger container with capacity 5, so there are 5, and just be careful. That might not be that case. You just take item 1, which volume or weight is 2, That's equal weight 2, so the capacity 3 goes to capacity 5. And you can fill that again. There will be 1, 2, 3, 4, 5. There are these 2, and there is this this previous fill. This previous fill. And of course, the same holds for item number 2, which volume is 3, which cost is 14. So you can get one from here, from this particular point. You can get by 1, 2, 3 to another fill of a knapsack, and the cost is 14. So now, of course, and the same holds absolutely everywhere in this graph. So now, when you start anywhere, and then you continue let's not anywhere. Start at the beginning, and then follow the edges. So what you do, you are in fact producing one of all possible fills of your knapsack of particular capacity. So if your capacity is only 9, for example, then you can start at the beginning and move to number 4. From there you can move to number 7, and from 7 you can move to 9. Like this one, and that's one possibility of filling this capacity 9. Now, because we have in fact put all the possibilities into the graph, that means that if we want to find the best filling of particular capacity, the optimum fill of our knapsack, what do we have to do? Well, we have to start at the beginning, move along the edges, arrive into the terminal node, and our path, the sum of all edges weights along our path should be maximized. You start with empty, and then you add 14, and then you, for example, again add 14, and then you add 9, and again you add 9. And you are there, you have arrived. The only question if it is the best path through that graph, the best in the sense of sum of the edge weights. We don't know, but now they say, okay, there is a directed acyclic graph, and what we have to do is only to find the most costly path. Is it so? Yeah. So what we want to do is finding, as they have said, finding the longest path in directed acyclic graph, where the length of the edge is, of course, its cost. So and we already last week we did that. The solution methods are absolutely identical. So strangely enough, the knapsack problem is a problem of finding the longest path in a directed acyclic graph, which is constructed very naturally. Each node corresponds to a capacity, and when you move from a node to a bigger capacity, you can move only along an edge which start and ends between two nodes, which distance in the graph corresponds to the size or to the weight of that particular item, and the weight of the edge or the cost of the edge is the same as cost of that item. And that's it. That's all. Of course. So now, how do you do it? Again, now the whole idea of finding the longest or the most costly path from the beginning to the end is repeated on this slide. And I think it's even on the next slide once more. So how do you do it? Of course, how to compute the value in the optimal value for the last node for the original knapsack. You look at the optimal values in all nodes which are connected by a directed edge to our current node which we are investigating, and we just look what are the optimum values in those nodes, and they were of course computed earlier. So what you do is just take again previous value, there is 18 as they inform us here. There was 18 plus 30, that's one possibility. Or you go here 6. What is the value there? There was 30. It was pre-computed. It is not in this picture, but you have to believe them. So 30 plus 16. That's another possibility, and so on. In total, 4 possibilities. Which one is the best? Well, it's I don't know. Probably the first one looks. 39 plus 9, there is another one as well. So that's it. The one possible path is here, and they tell you how to load the knapsack with maximum total cost 48, and that's it. How fast then can it be solved? Now the question is, okay, fine, the idea is nice. We construct a directed acyclic graph, run through the graph with a simple algorithm, and how long will that take? No, not that much. Not that much. Well, it's this graph. It has some number of nodes and it has some number of edges, and the whole process, the complexity of the whole process is proportional to the number of nodes plus number of edges, because each one is investigated, as I recall, only once each edge. This particular edge is investigated only once when we are considering how to get to node 10 from its predecessor. So each edge is only once visited. The number of edges typically is bigger than the number of nodes, so the number of edges is the most important parameter. And what is the number of edges in this graph? Well, if from each node there are edges going forward, as many edges as there are items. It does not hold for all from the in this at the end of the graph. You don't have the big edge with value 30 going out from, for example, here from node 8, but that does not matter. You might imagine that the obvious upper limit for the number of edges is the target capacity, which is in our case 10, maybe plus 1 because of 0, plus times the number of items, of course. There are k plus 1 less than we have n items. So this is capacity, and n is number of items. So we've got this. So the complexity is obviously just that number of capacity times number of items. Well, but that capacity, good. So it seems to be more or less linear. You plug in the capacity and plug in the number of items we've got, and there it is. Sometimes you will run into a little bit confusion, because if you go into literature or you discuss the problem with your colleagues, they tell you that this is the hard problem and no effective algorithm is known to solve it. Well, that looks completely ridiculous because, as we have seen, we've got nice and very effective method of solving the problem. Just go through the directed acyclic graph. More advanced colleague will tell you children in kindergarten do it all the day with no problem. Yeah, that might be right. Except for the kindergarten, but no effective algorithm is known. Why? We know that we can solve this problem quite nicely with the dynamic programming, but the time, of course, depends on capacity, on the capacity. The bigger the capacity, the longer the graph. So now you say, and what if the capacity is really big? So an example here, say, well, we can have a big capacity. That means like this, 2 to the power of 64. That's not that big number. It has less than 100 digits. It's relatively small. So this is this capacity. We've got this capacity of the knapsack, and then you construct your directed acyclic graph and run the program. So if the capacity K equals 2 to the 64. So you absolutely do the same stuff and solve the problem as we have done before. You put there 0, 1, 2, 3, 4, and so on, and there will be the edges going somewhere forward, not that much forward. You can see that the weight of particular items are relatively small, 2, 3, and 5 in this case. So you can go by a third, by 2, and by 5. There is 5 from 0 to 5, and so on. So you've got relatively short edges which go from each node and so on, and there your graph continues. There is your node 1000, 1001, and there is your node 1,000,000, and there is node 1,000,000 and 1 plus 999 with the edges down there, and there it continues and continues, and there is your node 54316994210, and there it continues until it arrives to 2 to the 64, which is, and there is 2 to the 64 minus 1, and so on. So there is this big graph. And the trouble is that it is, as you can see, it is really big. It starts there on the left side on the blackboard, and here on the right side of the blackboard, and it contains exactly this number of nodes, which you might think with our fast machines is not that big problem of processing, and you are some more or less right. Only the trouble is that you take 2 to the 64 and divide it by 10 to the power of 9, which is how many values you can fill in 1 second, more or less. In fact, on your probably notebook, it will be more or less less than 10 to the power of 9, 10 to the power of 8, and then of course the whole problem will be solved not in 500 years, but in 6,000 years, just to take it, because you've got how many? You've got 2 to the 64 divided by 10 to the 9, and that's the number of seconds, and just computing this should not be a problem. 2 to the 64 is 2 to the 60 times 2 to the 4, 2 to the 9, and 2 to the 60 is 2 to the 10 times 2 to the 10 times 2 to the 10 times, sorry, completely out of my mind. Of course, this is, excuse me, this equals 2 to the 10 times 2 to the 10 times 2 to the 10 times 2 to 30 times 2 to the power of 4 over 10 to the power of 3, 10 to the power of 3 times 10 to the power of 3. Surely enough. And then you say, okay, but 10 to the power of 2, it's about 1 kilo. So it is about 10 to the power of 3. This is 1024. This is 1000. So you say, we don't care about the details. So using this, you come to what you to cancelling these things, and you've got 2 to the 30 times 2 to the 4, and that is like you use the same trick. So you say it's the same as 10 to the 9 times 2 to the 4 is 16. So it is 16 billion seconds. And it's up to everybody to check how many years is this. Of course, therefore, they typically tell you, well, this means that the time depends on capacity, but that capacity, the number of nodes, or even better, that capacity is described by this number. That number is written down as a sequence of digits, and the number of digits is logarithmic with respect to the real size of the whole graph. Just imagine 10 to the 64 nodes here at the bottom of the blackboard, and that number, which is quite huge, is described by this tiny string containing just I don't know how many, about less than 20 digits. So therefore, to specify the whole problem, they give you the capacity and they give you these costs. In total, you've got less than 30 digits, and it specifies whole programs. You get 30 digits, and the result is about 600 years of computation. So obviously, the whole time you spend on solution is exponentially big with respect to the length of the string, which defines the whole problem. Don't forget to look at it in these two ways. We have absolutely effective method of solving the problem, but on the other hand, the effectivity is very good when the capacity is small. If the capacity gets bigger and bigger, then the effectivity exponentially drops down to in fact nearly nothing, no effectivity. Of course, this is far from effective. You're working 600 years, so you divide it into 600 computers, parallelize it somehow, and in 1 year you got the result. Okay, so this was example number 1, and we can jump into example number 2, number 3, and so forth. The next problem is exactly the same problem as we had so far, only that any item can be used at most once. So each item is unique. You can take only, and there, in the stock there is in fact only one of each item. So you are collecting some items which are, each of them is unique. You don't have this set, and that the problem is absolutely the same. We have to choose some items of those which are at our disposal in front of us and fill the knapsack with some of those items. How do we do it? And that is something they tell us something about the whole idea what to do here, but still first there is the description. So how many possibilities of filling our knapsack, not optimally, just putting something in there? How many possibilities are there? How many ways to fill it? Well, obviously you can each item either you use it or you don't use it. Now that means either you put it into your knapsack or you don't. So theoretically, you have 2 to the power of n possibilities. For one item, there are 2 possibilities, use or not use. For the next one, there is the same, use or not use. So 2 times 2 times 2 possibilities times 2 times 2, 2 to the power of n possibilities. So again, checking everything is impossible because this is exponential and it grows very fast. So again, similarly as before, we are going to produce a method which solves the problem. And okay, let's see how that works. Before we get there, there is again the example which just reminds us what we can do or we can expect. Again, we've got the same items here as before with the same characteristics, and there are 2, 4, 6, 8 times 2 is all 16 possibilities what can be done. Either we take nothing or we take all 4 items. They do not fit into our knapsack, so obviously this is not a valid solution. But the last 4 cases are not valid solutions, but all the previous ones are valid solutions, and some of them are the best ones. Probably this one is the best one. This is not no. This one is 46 is the maximum there. And we want to develop a method which will find exactly this solution. So the approach says, well, the approach is in fact very similar to the previous one. But now we cannot apply the same strategy, because in the previous strategy we could use some edges with the same weight more times. That means we could use some item more times. In this case, it is not possible, but still the idea says we can still somehow find a solution. So now again, we've got these knapsacks as before. All right, good. And we don't do the same to the knapsacks. We do the same to the set of items. We think about different sets of items. So we just don't have 1, 2, 3, 4. We can have a set of item, no item, item 1 and 2, item 1 and 2 and 3, and so forth. So now the strange and not quite obvious idea that it will work. So you fix some order of items. So you've got your knapsack there in front of you. There are these items. You take your knapsack and then you go along those items, and at each item you decide whether to put it into your knapsack or not. So it is slowly loaded. You omit some items, and maybe took some next one, omit this one, and finally when you come to the end, you have loaded your knapsack and be happy. So in this order you solve the problem, and of course when you are moving to the next item, you are using some optimal solutions from the from the previous steps. So that's the idea. So for each possible capacity of a knapsack and for each possible set of no, not possible set. For each subset in this order, solve the problem. And let us see how that works. So now it is a little bit complex because we've got a P is the problem, okay, with a set of items 1 to some, I don't know, 35 items. So if X is 8, so that means 1, 2, 3, 4, 5, 8, 7, 8 items, and not those further ones, and with particular capacity of your knapsack. So the node by optimum is the solution of that problem, and to solve, of course, that problem, use of optimal solution. Now this is critical. Optimal solutions of situations when you have just the number of items is just smaller by 1. So just imagine that you've got your knapsack, and you are thinking whether to include or not to include the item you are standing currently at. Then you say, okay, I've got only 2 possibilities. Either I include this item, well, if capacity is enough, or either don't include it, or just 2 possibilities what to do with particular item you are looking at the moment. And in each case, you can decide, because you can say, well, what is optimal now at this moment? Well, we can take this item and say, well, there are only 2 possibilities. We don't know at the moment which one is better, but you either take that item, either not. Either it is included or it is not. If you choose to take that item, if it is included, then what cost you arrive at? Well, the cost you will get is equal to the solution which considers just the item, all the previous items, and in which knapsack capacity is smaller by the weight of this particular item, of course. Now you say, well, if we take this item, then of course we have to look of loading the knapsack with capacity smaller by the size of that item, of course, and then do not forget to add the cost of that item because we are taking it. So it is exactly plus the cost of item X. So you take an optimal solution of the situation where you've got just by 1 item a smaller set. Or you don't include this particular item, and then of course you say, well, then nothing has changed from this previous step. Let us fill optimally our knapsack with items from 1 to X minus first, and of course the capacity does not change, because if that fits into some capacity that fits into their capacity, then of course now our capacity is bigger, and it will fit there as well. What to do? Now you can say, aha, so take into, either you take the previous element, so take the optimal solution of X minus 1 elements, and the capacity of the knapsack is our current capacity minus the volume of that elements which we have just included in our solution. That's 1, and of course do not forget to add the cost of that element. So that's 1 possibility. Either we do not include the current element, therefore we take the optimum of the previous X minus 1 elements with the same capacity. And now we've got now is something we have seen at the very beginning of our examples of dynamic programming last week, because this is 1 line function of 2 variables, x and y, and all the rest are just some constants, cx, vx, -1 are constants. We've got some optimal, some obvious solutions. When we've got a zero number of items, then of course our gain is 0, whatever the capacity of our knapsack is, that doesn't matter. Or if our capacity of knapsack is 0, then we cannot load anything into knapsack, then again we get 0. So there is, in fact, there is one simple table, and we have to fill the table, and we know some base, some easy values. So maybe I can now skip this whole stuff because it just repeats more or less what we already know, and jump directly into the example. There is we have two variables, x and y, and there is a table which is filled according to the formula 2 slides earlier. There is your formula. We know that the first, the 0th row and 0th column of our table should be zeros. So it is, and then what we do is we maximize. What do we maximize once more? X minus 1 and x minus 1. So this means if x is on the, not typically on those are a number of items. So x is on the vertical axis now. So this means look to the previous row and into which column? Either the same column as currently. So just when you are in some slots, just look at the slot which is at top of there, or look in the previous row and into where here is the position where to look. It is the same position minus the weight or the volume of that particular xth item. So what does that mean? Now they give us an example. So here is 25, how that was attained. So that means that we are just deliberating whether to include item number 3 into our knapsack of capacity 6. If it has capacity 6, you think, well, can we include, should or should not we include that item number 3. Item number 3 is this 1, 2, 3. So its weight is 4 and its cost is 16. So what you do, you say either we don't include it. If we don't include it, then of course we have used the optimal solution for up to for all items up to item number 2, don't consider current number 3. So that is on the previous line, and for the same capacity, because we have the same capacity, and say, no, number 3, don't include it. So that's the same as if we just took optimal solution of items up to 2, and somebody or the table tells us there is the number 23. Okay, so that's one possibility. Either we do include that item with number 3, and its volume is 4, or its weight is 4. So if our current capacity is 6, so that means if we include something which has weight equal to 4, therefore the previous capacity, optimally filled capacity with value 2, that means 6 minus 4. When we have capacity only 2, we can fill it somehow, and that fill will cost us the value of that fill will be 16. So that's the optimum. So now we add the third item, which has 16 is of the third item is its cost, boom, and we have to add that cost to 9, which was the previous optimal fill. 9 plus 16 is 25. 25 is bigger than 23. You take maximum of those two, and you arrive at 25. And you do the same and to any to each slot in this table. 44 was obtained in the same manner. 44, and there is 39. So either we don't include item number 4. That means with capacity 9, you can stack there something which total cost is 39, some arrangement of items from 1 to 3. Either you do, well, 44, either you include this item number 4, its weight is 6, from 9 you go 6 steps back to the left into the column number 3, and of course the items just up to 3, that optimal fill is 14. Now we are trying to add that element, that its cost is 30. 14 plus 30 is 40. 4, which is bigger than 39, therefore you store 39. Now, well, and this table just registers, this middle table just registers the optimal values. Of course, people also do want to know which particular items do you put there, so we have to keep track which elements we choose to put in our knapsack. So there is this table which takes track exactly of that. As you can see, each element knows that each element here is this table is derived from the element in the previous row. So therefore it is enough at each element to register from each column in this previous row it was derived. It was either this, when we are talking about the green ones, it was either this one, either this one. So you just put there 3, which is the column of the previous solution, which was extended, and we got there. The same holds here and so forth. So, for example, this 7 here down indicates that the optimal solution at that particular position was derived from the same column number 7, because there is 30, and if you try 30 minus, you are in the 7th column, so 1, 2, 3, 4, 5, 6, so there is 0 plus 30 will give you again 30, so there will be no improvement. So if those two values we are considering are the same in this function, this value and the second one are the same, that it does not matter which one we choose. So that's it. That's all. We just fill the table as we did at the very beginning and do nothing else. And where is our directive? So we have turned it into tabulation. Well, good. And where is our directed cyclic graph? Well, it is there, of course, because as you can see, there are some directed edges now, and we were, in fact, when we are filling these two tables, we are each time we are looking back along those green or blue directed edges here. So our directed cyclic graph looks exactly like this. There is each time there is one edge going to the next cell which is directly below, and of course it makes some steps into some previous column. It is shown in this picture, which looks rather terrible, but of course it isn't, because the structure is always the same. There are these vertical edges, and of course each this diagonal edge corresponds to the it's the distance between source and target node is of course the same as the weight or the volume of that particular item. Each item corresponds to one row in this table, exactly as before. So there it is. There are your items. Each item corresponds to one row, of course, and the length of the edge is exactly the volume of that item. Therefore, we've got, in fact, directed acyclic graph, and the weight of each edge, of course, is the cost of that particular item, which you are, in this case, when you go along the diagonal edge, that weight corresponds to the cost of that item. So you've got a graph which edges are weighted. It is directed and it is acyclic, because in each step you are just getting to the bottom and maybe sometimes to the left. So there are no loops in that graph, of course. There is your directed acyclic graph, and we process it in when you fill the table from first row, second row, next row, and so forth. Then you are in fact filling it in one of its topological orderings, of course, because you can put first row first, and from that first row you go just all the edges go into the second row, so they are further in the topological order, and so forth. So that means that in fact again we are processing the directed acyclic graph in the same way we did it in all previous examples. And that's it. Now the question is, what's the complexity of the whole stuff? And before that, of course, they just remind you that remembering the predecessors is exactly the same as I have just told you before. It is along the same edges, so you each time remember the chosen edge, which is highlighted here. So I will not go into that in too much detail. There is your 4, means that this optimum solution arrived from column number 4, 0, 1, 2, 3, 4. There's the 4. Here the optimal solution arrived from column number 3, so there it is, and so forth. So this is just the same idea all over again. Finally, this complexity. What is the complexity? The stuff is exactly the same as in the previous case when we had more items, more copies of items to use, because again our size of our graph up there again depends on the capacity of our knapsack. So in the previous example, we had just this one row here at the bottom, and in this case we have more rows. Each row corresponds to one item. So even if we don't have too many items, still if we have got a big capacity, then the size of the graph will be correspondingly big. So again, the complexity is absolutely the same as before. the capacity times the number of items. Of course, there are just 2 edges going out from each node, and maybe only 2 edges arriving into each node. So the number of edges is roughly twice big as the number of all nodes, and the number of nodes is obviously the capacity times the number of items. So the complexity is the same as we had before, and it is exponential with the respect of the string defining the capacity. So again, if the capacity is 2 to the 64, you've got this line, and if you've got 10 items, you've got 10 copies of this, and you have to process it. Again, take a long time. So that there we are with the complexity, and we finished another example of dynamic programming. So in the remaining 15 minutes, let's jump into, again, a totally different area, which surprisingly, again, will show us that we are talking about filling the dynamic programming table. The only thing is that I have to find it somewhere. Yeah. Let's jump there. Increasing subsequence. Yep. This is again a rather simply formulated and classical problem. What we have to do, totally different problem from some kind of linear algebra. They give us a few number of matrices. Those are, let's imagine they are just integer matrices or float matrices, does not matter. And they are relatively big, like sizes are 30 times 35, A4 is relatively small, it is 5 times 10, and the other matrices are big, just few matrices. We have to multiply all of them. And you say, well, they're not a big deal. Either you take your library, which multiplies matrices, and just plug in your matrices, and out comes the result. Or you do some analysis before and think what's going on there. If you want to apply these, multiply these matrices, you can in fact do it in different ways. So that we will see it in a moment. First of all, but I have to remind myself and maybe some of you as well how to multiply 2 matrices. Well, there is one matrix, there is the other matrix. How do you get a particular value in the result matrix? Well, it sits in some row and in some column. So you take a corresponding row in the first matrix, corresponding column in the second matrix, and then you do a scalar product of those 2 vectors. First element there times first element there, second element there times second element there, third element in the first vector, third element in the third vector, multiply them, and total the stuff. Obviously, if you have vector A and B, scalar product is the sum I equals to n, where n is of course the size of each vector. I times b, I equals 1 to n, excuse me. This is that is this, like that one. So that how many multiplications you have to do. The number of multiplications is equal to the length of those vectors. And of course, when you are multiplying the matrices, therefore it is obvious that the number of columns in the first matrix must be the same as the number of rows in the second matrix. So calculating product of two matrices of given size A times B, and the second is B times C, requires A times B times C multiplications. Why? Because there are A times C elements in the resulting matrix, and to calculate each element, you have to take the two vectors of length exactly B. So there it is, A times B times C multiplication. Then you say that we don't consider summation because the number of summations is more or less the same as the number of multiplications. And of course, each of those multiplications has to be performed by some processor, some unit which does the multiplication. So we are interested in question how long will the whole thing take before it is computed. So all right, rather tedious one, okay, multiplying matrices. But let's remember this formula, A times B times C multiplications, when we've got A, B, and C are sizes of those two matrices being multiplied. So now, okay, so what's the deal? The trouble is that the result, when we've got more than two matrices, the result can be computed in different order. Multiplication of matrices is associative, so you can first compute A1 times A2, then multiply the result by A3, get new result, then multiply that result by A4, and so forth, and you arrive to the result. Or you can start at the end, multiply 5 times A6, these last two multiply, and when you got it, then you from the left multiply it by A4. And when you've got the result of those three last matrices, then you can multiply it from the left by matrix A3 and so forth. And you can have a totally different order. You can start multiplying this here in the middle because they are smallest. It's the easiest thing to do. A3 times A4, you've got the result. Then you can multiply that by A5, and you've got this result, and then you can multiply it by A2 from the left, and by AC from the right, and by A1 from the left, and again you arrive. Each time, of course, because it's the multiplication which is associative, each time you arrive at exactly the same resulting matrix there, but of course the catch is that the number of operations you have to perform might be dramatically different. Why? Let's see the example on the next slide. Imagine you've got just three matrices down there, and these both cases have the same set and they completely same matrices. I don't put there the particular values which are in those matrices because the picture would be too much clutter or so. So you just have to imagine your favorite numbers in each slot. So there is matrix 3 times 5 of your beloved numbers, whatever they are, and the same holds for the remaining two matrices. So, and we want to multiply them all multiply them together. You can see that the number of columns in the first is the same as number of rows in the next matrices, and the number of columns in that matrix is the same as number of rows in the last matrix. All right, so what you do now, you either first multiply the first two matrices, get the result, and then take the without change, take the last matrix and then multiply those two to get the result. Or you can do it and start at the end. First you multiply the last two matrices and then get the result. As you can see, and graphically it is also suggestive that the two ways are different in the number of operations you have to perform. There are 3, 5, and 2, and the previous formula we had before tells us the number of multiplications we have to perform is 3 times 5 times times 2 here, which is 30. Okay, so we have done 30 operations. Then of course, taking the next matrix and multiplying with the result matrix, which is small, this result matrix of this operation, 3 times 2. So we have to say 3 times 2 times 4 is 24. Adding is 30 and 24 up there gives us 54 operations, and doing the reverse and doing the same calculations, 5 times 2 times 4 is 10 times 4 is 40. So this results in 40 operations. You've got this big matrix. This matrix is also big, so now you've got two big matrices. Size is 3, 5, and 5 and 4. So therefore, 3, 5, and 4, multiply them together. 15 times 4 is 60, so there you need 60 operation. So originally we had 40 to multiply those two. Now to get the remainder, we have to get the rest, we've got to perform 60, and there are your 100 operations at the top. So the order does matter. Therefore, in the previous example, there are many different possible orders in which we can do the stuff, and those orders, if we do the same scheme, not just for 3 matrices, but for 6 matrices, we arrive to those numbers. And there is, of course, one of them, one of many those possibilities, is the best one because it performs only 15, which is nearly just a quarter of the worst case. So it's a good idea to be able to choose the correct order of multiplication. How do we do it? I skip the details at the moment, and we have to multiply. Well, that's not that difficult because you say, okay, we have to compute this whole product. So, but that means that we put there some parentheses. We first compute some part and the next part, because what in the next step, in the last step, of course, you take, if you are, for example, here, in the last step, you are multiplying only 2 matrices, nothing else. And of course, those 2 matrices are the result of computing the products of first few matrices, then computing the product of the rest of those matrices, and getting some matrix on the left, get some matrix on the right, and then just multiplying those 2 matrices. So you have to, so now you say, okay, so let's imagine that we have an optimal solution, optimal ordering of multiplications in each of those blue areas which are on the screen. So we don't know the correct answer. So imagine we've got the correct or the optimal ways of ordering the products in all of these cases. If we got it, then we say, aha, so if we know this, then all we have to do is just to take those values and check which of those n-1 or how many lines is the best. Either we take the first matrix and take the optimal solution on the right of all remaining matrices and then multiply it together. But multiplying together has some cost. So there you take optimal solution there. You have to know what, and you will know, what is the size of this matrix, which is the result of the multiplication, and then you know the size of A1. So of course you can also compute the number of operations you have to perform by multiplying those 2 matrices. So so here should be this blue part should know how many operations, how many multiplications you have to do in optimal case to produce this thing. And of course, you had to add to that value the number of operations you have to do to calculate this product. And the same idea exactly holds for all the remaining rows. Therefore, you say, okay, if we have somehow pre-computed those blue areas, which again are smaller problems, they are the same, absolutely the same problem as the original one, only each of them is smaller, at least by one than the original one. So if we've got all those results, we can compute the cost of each row and choose the best of those, and that's our result, and nothing else. And okay, and how do you compute the results of those blue parts? Well, they are the same as the problems are the same. Of course, they have the same structure. So now you say, aha, so what's the deal? And the deal is on one of many other slides, which is somewhere because there are too many slides for this. I am afraid. They say that, okay, that the idea is, and that will be the last idea today, the idea is pre-compute turned into tabulation, of course, that's your basic idea. Pre-compute the optimal solution for each chain of subchain of matrix, subchain of matrices at recess for each subchain. And what is each subchain? Well, which starts at position, let's say L, and ends at position R. So we've got our matrices, which do not fit on the blackboard. We've got our that's not a good idea. We've got our matrices up there. So the various matrices in here, and for each subchain somewhere in the middle, from L to R, we pre-compute the optimal solution as if there were no remaining matrices. That's the same small problem as before, only it is smaller. So there we create our optimal solution. And knowing all possible optimal smaller solution and storing them in the table, we will be able to construct the solution of the original problem, because each subchain, each segment of those matrices is defined by its left and right position. So it is defined by two values, where of course L is smaller or equal to R. So each pair of indexes into the whole list of matrices define one subsequence. Therefore, our table again will be two-dimensional. We will store this pre-computation. We'll store the table. We'll store the result. Store the result at position at indexes indexes L, and R in the table. Yeah, so there you've got a table, and there will be L, there will be R, and that position, when you take this part and compute the pre-compute optimal solution and store it and that position in the table. How to manage the table we will see next time, because now it's 2:45, I think. So the idea then will be very simple. They show us to it there. Again, there will be some table which even is half filled with zeros, and we will somehow process the table in a direction which is not typical. So a little bit more different than in the previous cases, but that is for the next week. It is not for the next week, because next week is the substitution of holidays, I presume. So after 2 weeks, we will finish that. So thank you very much.